Yeah, so the first lightning talk is by Husein on quantum multi-user coordination. Please go ahead.
So hello everyone, my name is Husein Natur. I'm a PhD student of Professor Lossy from Technion. And today I'm going to present a poster about quantum multi-user coordination. So the problem is related to multiple topics that were presented today, like channel coding, and what also Matthew talked about, like the abstraction of multi-user networks, where we don't care about the specific implementation of the physical problem, but we care about the characterization of the quantum resources that we use in order to create a certain correlation. So I'll be presenting two posters. One is talking about quantum coordination in multi-user networks that are with quantum links. The communication is fully quantum, and the coordination criterion is the strong coordination. I'll explain exactly what that means. And the other one is talking about classical communication links. So in that case, we talk about empirical coordination, which is much more useful for multi-measurements and, for example, non-local games, where we care about the averages of the outcomes instead of a specific state. So I hope this gives you a general idea, and I will be ready for questions in the posters. So thank you.
Next is by Lossy from Compund. Her
Hello everyone, my name is Gabrielle Lalou. So as Aaron said, I'm a student from Telecom Paris Engineering School, and I did an internship, a research internship at the Technion in July. And so this research internship was alongside Husein and Uzi. And the goal was to find some ideas about how to find quantum secret sharing bonds on its capacity. And so first of all, what's secret sharing? So secret sharing is a way to encode and divide a secret among a certain number of participants with some secrecy constraints. And the main difference between classical and quantum is that in the classical secret sharing scheme, the secret is classical, known, and fixed. And in the quantum secret sharing capacity, the secret is an unknown arbitrary quantum state. And knowing that, how can we have an idea on having bonds on the secret sharing capacity for the quantum scheme? So there was a paper written in 2011, and in this paper, the authors had the idea to consider the quantum Wiretap channel, and because this channel was equivalent to the classical secret sharing problem, they could use the results from the compound Wiretap channel and adapt them to the classical secret sharing. So my idea here with Uzi and Husein was to consider the quantum compound channel and adapt its results to the quantum secret sharing with some quantum with some quantum broadcast channel results too. And so with that, we found some bonds on the quantum secret sharing rates.
So the next talk is by Ahmad Tahha. So he's a PhD student at Eurocom. He works in classical communication, and he works with Fedroselia and Dirya Malak.
Hello, everyone. My name is Ahmad. It's a pleasure to be among you today. Actually, what we are working is to make a general framework for distributed computation of non-linearly separable functions. And the goal is to design some actually encoding tensors and decoding matrices so that we can use them for a specific system design to achieve some actually some performance metrics that are satisfying some specific applications. I can actually explain in the poster session in detail. But at the summary, it's a transformation of the distributed computing problem to tensor factorization, which actually has lots of mathematical tools in discrete mathematics and combinatorics. Thank you very much.
Thank you. Okay, so the next talk is by Hadi Aghaee. He's with Braunschweig and TU Munich. His work is on network oblivious transfer, and I'll let him speak about it.
Hello, everyone. My name is Hadi. I am a PhD student at the TU Braunschweig under the supervision of Dr. Christian Deppe. My title is Network Oblivious Transfer and Information Theoretical View. In fact, we have developed the existing knowledge in oblivious transfer over noisy channel, point-to-point noisy channel, to the well-known networks in information theory, such as multiple access channel and broadcast channel. But at first, let's delve deeper into the simplest case of oblivious transfer between two parties, Alice and Bob. Alice is two separate strings or separate secrets and want to send them through a noisy channel to Bob, and Bob is only allowed to choose one of them and should be unaware of the unselected message, and also Alice should be unaware of the selected message by Bob. So this is a two-party secure computation, and it is well known that oblivious transfer is a complete cryptographic primitive. This means that if oblivious transfer is possible between two parties, then they can securely compute any functions between themselves. For example, they can compute bit commitment protocols, they can run secret key agreement protocols, and any other cryptographic primitives. At the first step, we have developed this simple model to multiple access channel with two senders and one receiver. And we have calculated the oblivious transfer capacity over this channel. And also, in the second step, we have developed this cryptographic model to the broadcast channel with one sender and two receivers. So at the moment, we can say that we are near to general theory of oblivious transfer in network information theory, but this is not the final goal. The final goal is to find the quantum advantage, if it is possible, for example, to share quantum entanglement between Alice 1 and Alice 2 in a multiple access channel, or any non-signaling correlation between two parties or three parties in multiple access channel. So at the moment, the project is going on in this step. So let's see for future if we can find the quantum advantage. And I cordially invite you to see my poster for further discussions.
Thank you. The next presenter is Nilesh Kumar. He's with TU Munich.
Hello, everyone. I'm Kumar Nilesh. I'm working with Holger Bokeh on hardware-based security, particularly quantum physically unclonable functions. This is actually a hardware device, just like fingerprints that uniquely identifies the device. But we look at PUF through information-theoretic sides, like how when we generate secret key or when we authenticate a PUF device, how secure it is, or when someone else tries to identify falsely, like we calculate false acceptance rate. And yeah, so basically in this poster, I'll be presenting different results. I think 5 or 6 results that I have done with Christian Deppe, Holger Bokeh, and Mark Geis also. All from information-theoretic perspective. We started with secret key generation when two parties want to generate, or the same person also wants to generate secret key at 2 different instants of time using quantum PUF. What is the capacity of the secret key? Then we also looked into authentication. When we want to authenticate a puff device, what is the false acceptance rate and how secure the authentication protocol is. And some other applications and practical challenges that we have discussed in our paper. And hopefully, and the other thing is the analysis is not that complex. It's based on channel coding and source coding. So we can discuss about it later in the poster session. Yep. Thank you.
Thank you. The next presentation is by Florian Seitz.
Thanks. Right. So the poster I'm presenting today is about a work that Yannis and I published at the ISIT this year called Capacity Formulas for the Lossy Bosonic Compund Wiretap channel. And so we're looking at a optical communication setting where we have loss, we have channel uncertainty in the form of a jammer, and we have a wiretapper all at the same time that tries to intercept the information. And now the question becomes, what guarantees can we make on the amount of information that the sender can reliably and securely get to the receiver? And so we prove the capacity formulas for the situation for different levels of channel knowledge of different parties. And what is perhaps, in my mind, the most interesting aspect is not so much the result itself, but the techniques and tools that are necessary to do this in continuous variables, which this, of course, is as a bosonic system. And then we also take this result and apply it to a satellite downlink scenario as a possible application of this theorem. So looking forward to seeing you at the poster.
Thank you. So the next one is by Fatma. She's a PhD student at Eurocom.
Thank you. Thank you. Thank you so much. So hello, everyone. I will just give a brief introduction on our work, me and Arun, and then goes to the details in front of the poster. So our work is on general classical communication channels. Specifically 3-user classical quantum and different channel and 3-user quantum broadcast channel. Traditional approach is relied on IAD random codes to derive inner bounds to the capacity rate region, but the inner bounds are not optimal. So some studies shows that structure codes like Coest codes can derive better inner bounds. So for that, I will use Coest codes to improve the inner bounds for 3-user classical quantum interference channel and 3-user quantum broadcast channel. But the challenge here is that in classical channels, simultaneous decoding is straightforward. But in quantum, it has been an open problem for decades, and recently has been solved by Sen, by introducing new noble tools called tilting, smoothing, and augmentation. But he has only developed this simultaneous decoding in quantum channels just for IAD random codes. So the challenge here is to analyze the simultaneous decoding with Coest codes, So that's it.
Okay, thank you. So the last one.